Welcome to GoFly Online. Today's flight lesson is the effects of controls. The aim of today's lesson is to teach you about the aircraft's primary and secondary controls. I will also be demonstrating the primary, further and secondary effect these controls have on the aircraft. An aircraft flies because the aircraft is able to generate a force known as lift. If we look at the cross-section of a wing, we can see the underside of the wing is flat and the top is curved. We call this cross-sectional shape of the wing an aerofoil. The aerofoil produces a lower pressure on the top of the wing, creating a net upward force known as lift. To create this pressure difference, three things need to happen. First, we need air to be flying over the wing. We call this relative airflow. Second, we need the wing to be curved. And third, we need the wing to be angled in relation to the relative airflow. We can increase the amount of lift we have available by increasing the velocity of the airflow over the wing, increasing the camber or shape of the wing, and increasing the angle of the wing in relation to the relative airflow. Lift is simply the force that directly opposes the weight of an aircraft and holds the aircraft in the air. A fixed-wing aircraft is known as a three-axis aircraft. A three-axis aircraft can move in three different axes: the lateral axis, the longitudinal axis, and the vertical axis. The aircraft pitches around the lateral axis, rolls around the longitudinal axis, and yaws around the vertical axis. The main control surfaces are the elevator, the ailerons, and the rudder. The elevator and ailerons are controlled with our control column or control stick, and the rudder is controlled by our rudder pedals. We also have secondary or support control surfaces known as the ancillary controls. Most light training aircraft have a control column or a control yoke. Normally operated with one hand, your flight instructor will advise what pressure is required for your particular aircraft controls. Some aircraft only require a very light touch, while others may require a more firm input on the controls. It is important to remember that during your flight training, the horizon is a primary visual reference at all times. As a visual pilot, your eye should be on the horizon for the majority of the time. The horizon is always a primary reference. We will now look at the primary effects of the elevator. The elevator is controlled by the forward and rearward movement of the yoke or control stick. When the control column is moved rearward, it deflects the elevator upwards. This deflection causes a downward force on the tail, which causes it to move down, which then causes the aircraft nose to pitch up in relation to the horizon. When you move the control column forward, this deflects the elevator downward. This deflection causes an upward force that moves the tail up and therefore pitches the nose of the aircraft down in relation to the horizon. The primary effect of the elevator is pitch. I will now demonstrate the primary effect of the ailerons. When we move the control column to the right, the left aileron moves down, causing a force upward, and the right aileron moves up, causing a force downward. This causes the aircraft to roll to the right. When we move the control column to the left, this causes the right aileron to move down, causing an upward force, and the left aileron to move up, causing a downward force, causing the aircraft to roll to the left. The primary effect of the ailerons is roll. I will now demonstrate the primary effect of the rudder. When we apply pressure on the right rudder pedal, the rudder will deflect to the right and create a force to the left, and the aircraft will yaw to the right. When we apply pressure to the left rudder pedal, the rudder will deflect to the left and create a force to the right, and the aircraft will yaw to the left. The primary effect of the rudder is yaw. Each of the primary controls will also have further or secondary effects. I will now demonstrate the further effect of the elevator. When the aircraft pitches up, the forces acting on the wing and the aircraft change, and as a result, the airspeed will decrease. When we pitch the nose down, the forces on the wing and the aircraft change, and the aircraft's airspeed will start to increase. The further effect of the elevator is airspeed. I will now demonstrate the secondary effect of the ailerons. The primary effect of the ailerons is roll. When we move the control column to the right, the aircraft rolls to the right. However, initially the nose will want to yaw slightly to the left. This is known as adverse yaw. Adverse yaw is caused by extra lift being produced by the upgoing wing, as when there is more lift, there is also more drag. This drag causes the aircraft to yaw in the opposite direction of the roll initially, then the yaw will stop once the bank angle is constant. Once the aircraft has rolled, due to the force of gravity, it will start to slip towards the lower wing. As the aircraft slips, the airflow increases rapidly against the side of the aircraft, and in particular the tail surface area of the aircraft, causing the aircraft to yaw in this direction as well. If we move the control column to the left, the aircraft will roll to the left. Initially, due to adverse yaw, the aircraft will yaw in the opposite direction of the roll. Due to the force of gravity, the aircraft will then slip towards the lower wing. The increased airflow over the tail area will cause the aircraft to yaw in this direction as well. The secondary effect of aileron is adverse yaw, slip, then yaw. I will now demonstrate the secondary effect of the rudder. When the pilot yaws the aircraft with rudder, in this example to the right, the inner wing experiences less exposure to the relative airflow than the outer wing. Also, the outer wing in the yaw will accelerating slightly more than the inner wing. This also creates more lift. This results in more lift being produced on the outer wing and less lift being produced on the inner wing during the yaw. Having more lift on the outer wing causes the aircraft to roll in the direction of the yaw. If this is left uncorrected, it may end up in a spiral dive. The secondary effect of the rudder is roll. We'll now look at the effect that the airspeed has on the aircraft. The airflow that moves over the aircraft while it is flying through the air produces a force on the aircraft. When a control surface is deflected, the control surface is exposed to the airflow, and this produces a force against the control surface. This force can normally be felt through the control column. At normal cruise speeds, where we spend most of our time, the aircraft designers have designed the controls to feel firm and responsive. When an aircraft flies at a lower airspeed, there is less airflow flowing over the aircraft and therefore less force on the control surfaces. This causes the control column to feel less firm and less responsive. We call this feeling sloppy or sloppy controls. When an aircraft flies at a higher airspeed, there is more airflow flowing over the aircraft and more force acting on the control surfaces. This force can be felt through the control column and makes the controls feel more firm and more responsive. You may hear this being referred to as fast and firm. During some stages of flight, for instance on takeoff, we have more airflow being produced by the slipstream of the propeller. This propeller slipstream may make the elevator and rudder that are exposed to this slipstream feel firm and responsive even if you are flying at a lower airspeed. The ailerons, being situated outside of the propeller slipstream, may still feel sloppy. So in this example on takeoff, the rudder and elevator could feel firm and responsive, and the ailerons feel less firm or sloppy. So in summary, in relation to the effect that airspeed has on the aircraft, at higher airspeeds, the controls feel more firm and more responsive, and at lower airspeeds, the controls feel less firm and less responsive or sloppy. I will now demonstrate the effect that power and the propeller slipstream has on the aircraft. We will firstly assume that the aircraft has a fixed pitch propeller, meaning the propeller blade angle cannot be changed during flight and therefore the the propeller has a direct relationship with the engine. The propeller produces a force called thrust that results in the aircraft being able to accelerate and move through the air. This airflow, due to the rotation of the propeller, starts to rotate around the aircraft fuselage. In most light training aircraft, the propeller moves clockwise from the pilot's point of view. This airflow results in more force on the rudder area, usually on the left-hand side. This causes the aircraft to yaw left. The aircraft designers have designed the aircraft to have either the rudder or engine and propeller slightly offset, so in normal cruise, where the aircraft spends most of its time, the aircraft does not yaw left and will fly straight. When power is increased, the slipstream and resulting force will increase in the tail of the aircraft and cause the aircraft to yaw left. When power is decreased, the aircraft will have less slipstream and force on the tail and a tendency to yaw to the right. Another factor or effect is when we increase power and propeller slipstream, we increase the airflow over the inboard section of the wings, which increases the lift or force on the wings and more downward lift or force on the elevator. Also, when you increase thrust, the resultant force of the propeller is directed forward. This creates a moment around the center of gravity. This has the effect of causing the aircraft to pitch up. If we reduce power, we now have less thrust being produced and less airflow over our wing and elevator. Also, a pitching moment is created around the center of gravity due to the reduced thrust. This results in the aircraft pitching down when we reduce power. If we add these effects together, we can see with a clockwise rotating propeller, when we increase power, the nose pitches up and yaws left. And when we decrease power, the nose pitches down and yaws right. Most aircraft have ancillary or secondary controls, the main ones being flaps and trim. The flaps are a lift generating device. When we select flaps, we are actually changing the shape of our wing. If we look at the cross section of a wing, we can see that the top of the wing is curved compared to the underside of the wing. We call this curvature camber. When we increase our camber, we increase the amount of lift being produced. When we select flaps, this increases the camber and thus increases the lift. Having flaps on an aircraft allows us to produce more lift and take off and land at a slower speed. The flaps are a lift generating device. A trim tab is a tab attached to a control surface, normally with a hinge, and can be attached to the elevator, ailerons, and rudder. They can be manually ground adjustable or in-flight adjustable. In most light training aircraft, only the elevator has an in-flight adjustable trim tab. Let's assume we are flying, we have moved the control column rearward. This deflects the elevator up and produces more downward force or lift to pitch the aircraft nose up. The relative airflow striking the elevator will also want to force the elevator to return to the neutral position. The pilot could hold the elevator in position, however, they would feel the force through the control column or yoke. This force or pressure on the controls could get quite tiring for the pilot during certain phases of flight. To reduce this pressure on the controls and to stop the control surface moving, the aircraft designers have designed what is known as a trim tab. The trim tab can be controlled in the cockpit with either a trim wheel or an electric trim button. The trim tab simply acts like a smaller wing at the rear of the elevator and creates a force opposing the elevator to keep the elevator in the required position for a particular maneuver. Once the trim tab is in the correct position, the elevator will stay in this position and the pilot will now not feel any force in relation to the elevator. Think of the trim tab as producing an opposing force to that particular control surface. From the cockpit, all the pilot has to remember is that you have up trim and down trim. If the pilot feels pressure on the control column and the control wants to move forward and the aircraft wants to pitch down, then there is too much down trim. If the aircraft wants to pitch up and the control column wants to move rearward, there is too much up trim. To alleviate the control column pressure, when the aircraft wants to pitch down and the control column wants to move forward, you simply use up trim to reduce the control column pressure. To alleviate the control column pressure when the aircraft wants to pitch up and the control column wants to move rearward, you have to use down trim to reduce the control column pressure. Trim is used to reduce the control column pressure for the pilot. Remember, do not fly the aircraft using trim. We fly using the control column and elevator to control our pitch and use trim to simply remove any unwanted pressure on the control column. Most modern training aircraft are powered by a 4-stroke, 4-cylinder, horizontally opposed cylinder engine. The future will most likely contain a mix of petrol, diesel and/or electric engines, but still the majority of modern training aircraft use either avgas, MOGAS or diesel fuel. Most training aircraft engines use either a carburetor to mix the fuel and air before entering the engine cylinder, or fuel injection to inject the fuel-air mixture into the engine cylinders. Most light aircraft engines are air-cooled, however some aircraft engines, such as the ROTAC series of engines, are liquid-cooled. One common issue with carburetor engines is the possibility that ice can form in the carburetor. The carburetor mixes fuel and air together before it enters the engine cylinder. Under certain conditions, ice can form in the carburetor. Aircraft designers have designed a carburetor control that, when selected, injects hot air into the carburetor to prevent ice from forming, or if ice has formed, to melt the ice. Many aircraft engines also have mixture controls. This is a manual control to control the amount of fuel to air mixture that goes into the engine. As you climb in an aircraft, the air becomes less dense, and the pilot may have to reduce the amount of fuel being mixed in the engine to make sure the fuel and air mixture remain constant. The pilot controls the fuel-air mixture with the mixture control. The throttle controls the amount of fuel and air mixture being distributed to the aircraft engine cylinders for combustion. To increase power, advance the throttle forward, and to decrease power, move the throttle rearward. Most light aircraft engines are air-cooled. However, some aircraft engines, such as the ROTAC series of aero engines, are liquid-cooled. Most training aircraft have a fixed pitch propeller, meaning the propeller pitch is fixed and cannot be changed in flight. Some aircraft have a constant speed or variable speed propeller, meaning the propeller can be changed on the ground or in flight manually with a constant speed control unit. For a fixed pitch propeller, when we increase power, we increase the propeller RPM, which increases the thrust of the aircraft. The main controls a pilot will use on the ground are the throttle, brakes, and steering controls. Aircraft brakes, depending on the aircraft, may be foot brakes or a handbrake. Toe brakes are normally situated on the top of the rudder pedals and require pressure from the top of the pilot's feet to activate them. With toe brake aircraft, it is important the pilot's heels are on the ground so they do not accidentally activate the brakes on landing or takeoff. Some training aircraft have a handbrake, and this is normally activated by pulling on the handbrake to increase the brake pressure. Most training aircraft have a steerable nose wheel that is connected to the rudder and steered with the rudder pedals. To move to the right, the pilot applies pressure to the right rudder pedal, and to move to the left, the pilot applies pressure to the left rudder pedal. Some aircraft have a cast-ring nose wheel. This means the nose wheel moves freely. With a cast-ring nose wheel aircraft, the pilot has to use differential braking to turn the aircraft. To turn the aircraft, the pilot applies more right brake to turn right and more left brake to turn left. The pilot applies pressure evenly to both brakes to slow down or stop. Most training aircraft have a fixed undercarriage, which means the landing gear is permanently fixed into position. More complex aircraft may have a retractable undercarriage, which is retracted when flying. It's important when starting the aircraft to make sure there are no other aircraft, persons or objects behind the aircraft. Just before starting the aircraft, the pilot should clearly yell out the window, "Clear prop," to warn anyone in the vicinity that the engine and propeller is about to start. Airmanship is the proper use of prior learning, experience, and reliable information to make good decisions when flying, to mitigate risks, and to safely accomplish the flight objectives. The term human factors pertains to the pilot's physical and psychological state and how these states affect the safety of the flight. Threat and error management in relation to the CASA definition refers to the process of detecting and responding to threats and errors to ensure that the ensuing outcome is inconsequential. In other words, that the error does not lead to an undesired state. When it comes to flying, we have different types of threats we have to consider. Environmental threats, such as adverse weather, other aircraft and terrain. Operational threats, such as aircraft malfunctions or maintenance errors. Latent threats, such as training deficiencies. Internal threats, such as stress and fatigue. During each lesson, we'll be identifying the human factor elements and ways to reduce any threat and error. Before going flying, the pilot and/or student pilot needs to complete a personal checklist to make sure they are fit to fly. We call this checklist the I'm Safe checklist. I is for illness. Have you had any illness or symptoms of illness lately? M is for medication. Have you taken any medication that may affect your ability to fly? S is for stress. Are you under any stress that could affect your ability to fly? A is for alcohol. Have you been drinking alcohol in the last 48 hours which may affect your ability to fly? F is fatigue. Are you feeling tired and are you adequately rested? E is for emotion and eating. How are you feeling emotionally and have you eaten appropriate food and are you adequately hydrated? During your flight training, it is also important to know whether the flight instructor or student is in charge of flying the aircraft at any time. When the instructor wants the student to have the controls, they will say, "You have control." And when the student takes the controls, they will respond with, "I have control." When the instructor wants to take the controls back, they will say, "I have control." And the student will say, "You have control," when they have handed the controls back to the instructor. It is important to always make sure the instructor has control of the aircraft before the student removes their hands and feet from the controls. All aircraft differ in how the control column or control yoke should be held by the pilot. Please consult your flight instructor for your particular aircraft type. Well, thanks for completing the Effects Controls pre-flight briefing. Please complete the Effects Controls quiz to test your knowledge. Happy and safe flying, and see you next time on GoFly Online.